get my screen up here in a minute. Just give me 1 second, folks. Good. Now I need to do a little bit of reorganizing. Okay, so welcome, colleagues, to the third of 4 lectures on program effectiveness research. And recall, if you don't mind, what we have covered in previous lectures. So you will recall that lecture 1 discussed how program effectiveness research is grounded in program logic models, and how those program logic models shape the research questions that get asked by program effectiveness researchers. Lecture 2 discussed the potential outcomes framework for assessing program effects on outcomes and how various research designs that are used by program effectiveness researchers are consistent with that framework. Today, lecture 3 is going to turn to questions of how to estimate and interpret various types of program effects in order to assess the confirmation status of a program's logic model. Now, a reminder once again about the nature of this lecture series. Today, in particular, I'm going to cover several topics. It's my opinion that even though the material today might seem to you to be particularly dense, the topics actually haven't or aren't going to be covered in a lot of detail. And as always, my emphasis today is more on conceptual understanding than on the statistical analysis required to estimate program effects. Again, I'm emphasizing conceptual understanding because my goal is to point attendees to topics in the field that they need to attend to, and to encourage them to study those topics more deeply in order to be able to conduct program effectiveness research independently. So there's no expectation here that you can listen to my lecture for a couple of hours and actually be able to do what we're talking about, but you will certainly know what the language of program effectiveness research is and where you need to study. As in the past lectures, I have at the end of this lecture slides, a single slide that points you to some resources I think you can use that will help you develop deeper knowledge about today's topics. These are basically overviews such as the one I am presenting, with references to the academic literature and also to statistical software that can help you do some of the things we're talking about. And today's lecture in particular is actually fairly amenable to getting further information through simple Google searches. So for example, I'm going to talk about effects that have common names like the Itt effect or mediation effects. And if you Google, just do a Google search, how to estimate an Itt effect using, and then plug in your favorite statistical software program, you'll actually turn up a lot of information about how to use data and analyze it to get the effect estimates that I'm talking about today. So one final reminder, we have limited opportunity for audience participation today. I'm going to lecture for about 90 minutes, and then we'll have at the end of that period a Q&A session. So hold your questions until the end of the lecture portion. When we move into the Q&A section, we'll use the Zoom Q&A function to answer questions. And I do ask that you hold the comments to all in the Zoom chat box while I'm talking, because those pop up on my screen and sort of interfere with my ability to see what I am, see my own slides. So that's the format. Let's shift now to what are we going to talk about today. So what I'm going to do today is define different kinds of treatment effects that are almost always discussed in the causal inference literature. Now, these have names, so the names of the effects we're going to discuss are the intent to treat effect, the effect of actually receiving treatment, which is I'm going to call the effect of treatment untreated, conditional average effects, which I will call CATE, and the average causal mediation effect, which I'm going to call ACME, because these are the terms that get used. So what I want to do today, in addition to explain to you what these effects are and why you would want to use them, I'm going to explain how those different treatment effects can be used to examine the confirmation status of a program logic model. Now recall, a program logic model is a program's theory of action, and program effectiveness researchers are designing research to see whether, in fact, the program operates as theorized. And so the tests are tests of the confirmation status of the logic model. Does it work as you expect it to work? And so the proviso I have about today's lecture is this. Some of the effects that I am going to discuss today can only be estimated under or estimated with a lot of assumptions. So these effects are complex and they're assumption laden. And so in the summary and overall, I want to emphasize that it's probably best to keep analyses simple and only move to these more complex analyses that I'm going to discuss when it's truly warranted. That is, I'm not advocating here that you do a set of complex analyses. In fact, I prefer simple analyses, and I will at the end describe the conditions under which the simplest forms of analyses are just fine. But there are occasions where these more complex forms are warranted, and so I'm going to introduce them. Importantly, and this is important, I am not going to cover three topics that are statistical in nature and related to the estimation of these effects. So one is, whenever you estimate an effect, you're probably going to try to see whether or not it is statistically significant. And statistical significance involves precision in estimation. And I am not going to talk about how to improve the precision of these estimates, but it is an important topic that as you move to actually doing research, you need to think carefully about. I'm also not going to talk about how to improve the statistical power of a study design so that you can assure yourself that you can really detect statistically significant effects of the size you wish to detect. Statistical power is an important part of research planning, but I will not be discussing that today. And finally, and this has come up several times in the Q&A sessions of this lecture series, I'm not going to discuss how the multi-level nature of data affects the precision of estimates or power in particular studies. All of those topics are important, and you probably, if you are going to engage yourself in this kind of research, you should familiarize yourself. But they're of sufficient complexity that they really warrant a whole nother lecture series. And so I'm just going to stay at a more conceptual level today. So let me begin here now by bridging from the previous lectures to today's lecture. You will recall that program effectiveness research is all about the confirmation status of a logic model. And you will recall that a logic model is really implicitly a set of hypotheses about how the services that an intervention program delivers to units, which I am going to call today the treatment, affects a set of implementation processes in those treated units, and in turn, how those implementation processes then affect a set of final program outcomes. So the example which we have been using throughout this lecture series is a program logic model for an intervention that intends to use professional learning communities to improve student learning. And as we discussed in lecture 1, that model would have 3 components: a service delivery model that defines the treatment that is going to be given to enrolled units. And so the program says, here are the services we are going to deliver. It lists them, and that defines the treatment. The program then has what I have been calling an implementation model that defines what it is that units are expected to do as a result of treatment. In the professional community case, that will be both a set of structures and processes by which the professional community will operate, and some expected effects on teaching and learning activities in classrooms. And then the program specifies a set of intended outcomes. That's the outcomes model. So that's the idea of a logic model, which we have discussed on several occasions in this lecture series. Now, what I'm going to do today is focus on 2 types of effects that really test the confirmation status of a logic model. The first are types of effects that express the extent to which the service delivery model directly affects outcome models. So this is going to be the ITT effect, the TOT effect, and the Kate effects, and I'll discuss what those are here in a minute. But part of this is just about estimating direct effects of service delivery on outcomes and treating what happens as a result of service delivery more or less as a black box to be investigated later. The second type of effect that I'm going to discuss actually gets inside of that black box to investigate how implementation processes result from the service delivery model, and examines the extent to which those implementation processes affect outcome models. That's the average causal mediation effect by the language of causal effects that we're going to be discussing today. So let's review here. I'm going to call the 3 types of effects discussed today the intent to treat effect, the ITT, the effect of treatment on treated. I'm going to sometimes use the language TOT, the acronym. Conditional average treatment effects, I'm going to call those CATES every once in a while. And average causal mediation effects, I'm going to abbreviate that ACME, and I'm going to say it as ACME sometimes. So sometimes I'll use the full word, sometimes I'll just be using those little acronyms. What I'm going to do is first describe how information about services delivered to treated and untreated units in a study can be used to decide whether to report an ITT estimate of program effects on outcomes or a TOT estimate. I'll then discuss how to estimate CATES to assess whether program effects on outcomes are uniform across subgroups in a study. And finally, I'll discuss how mediation analysis can be used to examine whether program effects on outcomes are explained away by implementation processes. So let's keep going on the bridge. Recall also the potential outcomes framework. So recall that we have previously defined a treatment effect as the difference between 2 potential outcomes. One, the outcome that a unit would receive if it were treated, and the other, the outcome it would receive if it were not treated. And so on this view, the average causal effect over a number of subjects would be the expected value of the outcome under treatment minus the expected value of the treatment under control conditions. And what we're going to do today is refine our thinking about that tau average in a variety of ways that better reflect how the real world and scientific research operates. So in doing so, we're going to extend our thinking about the average treatment effect in three ways. The first important point I'm going to make is that there is a distinction between being assigned to a treatment group and actually receiving treatment. So here we're going to allow for the possibility that units that get assigned to treatment might not actually receive treatment. And we're going to allow for the possibility that units in the control group might actually receive treatment despite the fact that they were assigned to the control group. And knowing that, having data on that and knowing that will allow us to define two different types of average treatment effects. The intent to treat effect, ITT, is the effect on program outcomes simply of being assigned to the treatment. And the Complier average treatment effect, or the effect of treatment on treated, the TOT effect, is the effect of actually receiving treatment on program outcomes, given that the unit was assigned to treatment. So we're going to make a distinction between being assigned to treatment and receiving it, and we're going to estimate two different kinds of average causal effects for programs, depending on whether it's just taking into account assignment to treatment or actual receipt of treatment. In the next step, we're going to allow the treatment effects to vary across predefined subgroups of the population being studied. So here we're no longer going to assume that there's a single average treatment effect that is constant across all units in a study. We're rather going to allow for heterogeneity in treatment effects. In particular, we're going to test for the idea that there are different effects, sizes, depending that are occurring in different population subgroups. That's the conditional average treatment effect. And in the final part of this lecture, we're going to allow for the possibility that some post-treatment outcome, in our case, implementation processes, affect program outcomes, and that process, the post-treatment outcome, explains, at least in part, the direct effect of assignment to treatment on outcomes. So the post-treatment outcome that I'm going to focus on is implementation processes, and this is where we test whether our theory of implementation is actually germane to the outcomes being produced. So again, the purpose is to discuss how to estimate different types of treatment effects and use that to confirm a logic model. In the first part of the lecture, I'm going to be talking about the intent to treat versus the treatment on treated, which is all about whether or not a unit assigned to treatment received treatment. In the next, we're going to allow treatment effects to vary across subgroups in our study, and then that's called the conditional average treatment effect. And in the third part of the study, I'm going to talk about how you can examine the presence of implementation variables in both treatment and control groups and how to use data on that to estimate an average causal mediation effect of program implementation on outcomes. So here we go. Let's start with the intent to treat versus the effects of treatment on treated. Now, this is often discussed in the causal inference literature as a problem of compliance. So let me discuss the compliance problem as it occurs. And by the way, the compliance problem in research can appear in both the treatment group and the control group. Let's start with compliance problems in the treatment group. So it turns out in both the real world and in experiments, the units that get assigned to treatment sometimes don't comply with their treatment assignment. Now, sometimes this occurs in the real world and in research because the treatment follows what's called an encouragement design. So in this encouragement design, units that are assigned to treatment get invited or incentivized to take up a treatment, but they're not forced to do so. So for example, something all of us are familiar with, doctors write prescriptions to patients encouraging them to take medicine. But patients might or might not take those medicines. Or sometimes policymakers offer incentives for schools to adopt programs, but not all schools adopt the program. Or in the real world, sometimes individuals or organizations contract with intervention programs for services, but for a variety of reasons, they never actually use those services. That is actually quite common. These compliance problems are mirrored in studies. Sometimes researchers obtain agreements to provide services to units in the treatment arm of the study, but sometimes those units that get assigned to treatment simply decide not to participate or take up the treatment. In other cases, researchers actually use an encouragement design where units are assigned to treatment and then encouraged through incentives to take up treatment. So in both the real world and in research, intent to treat is not necessarily the same thing as receipt of treatment. Now, compliance problems also occur in the control group. And so let me just talk a little bit about how that occurs. There are two kinds. If you go into research studies, you might find that a treatment gets adopted by units that have been assigned to the control group. And that's a form of non-compliance, sort of the inverse of the non-compliance that one would observe if you're observed to treatment and don't take it up, or now you're observed to the control group but actually take up treatment. That's another form of non-compliance. Now, in research, non-compliance is unlikely if the treatment under study is unique and available only to the treated group. So experimental medicines, maybe some of you have enrolled in experimental treatments in a hospital and know that you are not able to get that treatment because it's not approved. The only place you can get it is under treatment. Those studies don't have non-compliance problems, but other times the treatment isn't particularly unique and it's actually available to control units. So let's consider some examples from research. Sometimes we are studying intervention programs that are actually widely disseminated. So at the recruitment stage of a study, we make sure that what we recruit are units that have never participated in the treatment, and then we assign those units to treatment and control. A problem occurs if over the course of the study, some of the units assigned to the control group actually secure treatment outside the study protocol, and that can happen. And alternatively, we might be using an encouragement design, and so we assign units to treatment and control and encourage the treatment units to enroll in treatment. But we're not encouraging control group units, but some control group units might actually end up enrolling in the treatment. So the classic case of this is the experiments which capitalize on the fact that private schools are over-enrolled, run lottery experiments that randomly assign people to be able to attend the private school or not. And occasionally people in the control group who can't go to the private school they were lotterized on end up going to another private school, and so we have non-compliance. So again, we can have non-compliance in the treatment group, and we can have non-compliance in the control group. So the key point here is that the effect estimates that we can envision may or may not take this non-compliance problem into account. And so this is where we begin to amend our thinking about how to estimate the average causal effect of a program. So to begin, let's define two indicators of treatment. One, let's just denote here for our purposes with a T, where T is 1 if the unit is assigned to treatment and 0 if assigned to control. And another is called D, where D is 1 if the unit actually participates in the treatment and 0 otherwise. So in the intent to treat analysis, what we do is compare outcomes across units assigned and not assigned to treatment, regardless of their compliance status. So an ITT analysis is simply the expected value of outcomes where treatment was assigned minus the expected value of outcomes where the unit was assigned to the control group. By contrast, the effect of treatment on treated involves comparing outcomes across those who were assigned to treatment and participated. Treatment equals 1, treatment assignment equals 1, treatment take-up equals 1, versus those who were not assigned to treatment and did not participate in treatment. Treatment assignment equals 0, treatment take-up equals 0. So the treatment on treated effect is the expected value of an outcome given you were assigned to treatment and experienced the treatment minus the effects summed across those who were not assigned to treatment and did not participate in treatment. Okay, so those are the formal definitions of the ITT and the TOT. And the key to estimating TOT effects is to always gather data on service delivery in both the treatment and the control units in the study so you can assess compliance status. And by the way, you'll recall from lecture 1 that I discussed the importance of having a clear service delivery model, not only as a matter of principle of operation for an intervention program, but you can see that in research now, the service delivery model defines what the treatment actually is. And so measuring whether specified services were delivered to units in both the treatment and the control group is important for us because that's how we're going to determine whether a unit actually participated in treatment. So when we gather data on service delivery in both treatment and control, we're in a position to describe, or as you'll see, infer the compliance status of units in a study. Now, what I'm going to do right now is describe the various ways that the causal inference literature has discussed compliance and non-compliance. So in the literature on causal inference, units in a study are assumed to have predispositions towards taking up treatment or not. And that word predispositions is important because these predispositions are assumed to exist prior to assignment to treatment. And 4 predispositions are described, and so those are described in the left-hand most column of the table. And the expected outcome of having this predisposition on whether or not you take up treatment is what's in the cells of this table. So the one group of people are predisposed to be clients, compliers, and compliers will always follow their assigned condition. So if they're assigned to treatment, they'll take up the treatment. If they're assigned to control, they won't take up the treatment. Another group of people, excuse me, are predisposed to always seek out the treatment regardless of what condition they get assigned to. That the literature calls these individuals always takers. So an always taker will always be treated, whether assigned to treatment or assigned to control. Then we have people who are predisposed to never take a treatment. So never takers will, regardless of assignment, not take up the treatment. And then there are defiers who will do the opposite of what they are assigned. Okay, so the causal inference literature next makes a set of assumptions about how to estimate program effects on outcomes, given that individuals or units in a study have these predispositions. So these assumptions are, first of all, that assignment to the treatment or control group was done through random assignment. And this is an important assumption because if random assignment is used, the proportions of compliers, always takers, never takers, and defiers should be the same in the treatment and the control groups. The second is that random assignment to treatment always increases the likelihood of treatment participation. The third is that the usual assumption, no interference, the outcomes of any individual are not affected by the assignment of somebody else. The third is that outcomes actually respond to receipt of treatment, not assignment to treatment. So the effect of treatment receipt is the same, whether you're in the treatment or the control group. And the effect of non-receipt of treatment is the same, whether you're in treatment or control. And in both cases, or in this case, the treatment, non-receipt of treatment is always has a zero effect. And the other assumption, which is an important one, kind of an exclusion restriction, there are no defiers assumed to be in any study. So we have these assumptions, and now this allows us to better understand, and as we're going to see in a moment, to actually estimate an ITT or a TOT effect. So suppose, and we're operating now in a hypothetical world, that we could actually observe and know each unit's predisposition towards compliance. So in the table below, we see we have 40 individuals or units assigned to treatment and 40 assigned to control. And we see that there's a distribution of compliers, always takers, and never takers in this study population. We see that the distribution of those compliance predisposition types is the same in the treatment and control group. In the hypothetical I have here, about 75% of the units in the study are compliers. Another 12.5% are always takers, another 12.5% are never takers, and by assumption, there aren't any defiers. Okay, so that's the basic setup. And if you look, we are going to calculate now tau average, not across the entire population, but for each subgroup. So if we have outcomes on these units and we calculate a treatment effect for each of the subgroups, we have what's known as a local average treatment effect. So, for example, in the table below, we have people who are compliers. In the control group, they've been treated, or in the treatment group, they've been treated. In the control group, they've not been treated. And the difference in outcomes for that subgroup is 20. And that's the complier average treatment effect. We notice that the always takers are always treated no matter what group they're in, so their effect is 0. We notice that those who are not treated are never, the never takers are never treated, and so they're 0. And so what we have is a complier average treatment effect of 20, and that is the effect of treatment on treated given compliance, and that's what a TOT effect is. Now, we can also use these data to calculate what the intent to treat effect is. So you recall that the ITT is the effect of being assigned to treatment, whether or not you participated in it. And so in this sense, it's the comparison of treatment effects across all subjects in treatment and control, regardless of their compliance status or predisposition. And from a table like this, the ITT can be calculated as a weighted average of each of the local treatment effects. So since 75% of the subjects are compliers and 12.5% are always takers and 12.5% are never takers, the average treatment effect is the sum of 75% times 20 plus 0% times 12.5, 0 effect times 12.5%. And so we see that the ITT in this little hypothetical table is 15. Okay, so the TOT effect, again, is 20 and is defined formally only for the very first row of the table, the compliance average treatment effect. And that's because if you think about it from the potential outcomes framework, the always takers have no counterfactual. They are always treated. And the never takers have no counterfactual because they are never treated, and we're assuming away the problem of defiance. So again, we see that the average complier average treatment effect is 20, and that's larger than the ITT. And there's a little note here, if you don't understand weighted averages, it really, if we had different weights assigned to this, we'd still get the same TOT, and we'd still get the same complier average treatment effect. So a problem in the real world is that we in fact don't know in advance what the compliance predisposition of any individual unit is. However, because of random assignment, we can assume that compliance predispositions are equally distributed across treatment and control. If we're using random assignment, we can assume that the predispositions are equally distributed across treatment and control. And knowing that, we can use data on service delivery to estimate the TOT in a given study. So the empirical problem is to identify the percentage of compliers in the treatment group. Because as we saw, if we divide the ITT by the percentage of compliers, we actually get the effect of treatment on treated. Excuse me here, right. So how do we do that? Well, let's go to a world in which we don't know the predispositions, but we have collected data on whether or not a unit actually took up and received treatment. To identify the percentage of compliers in the treatment group, we just use some data on service delivery. For example, going back to that table and now assuming that it was based on data, we would know that 35 units in the treatment group received treatment. Okay, we would know that because we would have data that, but we wouldn't know whether those units were compliers or always takers. If, however, we also had data on service delivery in the control group, we would know that 5 units in the control group received treatment, and moreover, we would know that they have to be always takers. So because of random assignment and the equal distribution of compliance types across treatment and control, we can now actually figure that the number of always takers in the treatment group is 5, because that's what it is in the control group. that would make the number of compliers 25. So if we had an ITT effect and divided it by this percent of compliers in the treatment group, we would get the TOT effect. And in our case, that's 15 divided by 0.75, and it equals 20. So the trick here is have data, estimate, use that data to determine who got treatment in the control group and who got treatment in the treatment group. Subtract the number of people who got treated in the control group from the number who got treated in the treatment group. Divide the ITT by the percentage of people in the control group who got treated, and you have the TOT. So we've just defined two kinds of treatment effects, the ITT and the TOT. And again, let's just review. The ITT is the effect expected from being assigned to treatment. And it's important to remember that whenever you have an ITT effect, the treatment group might include units that were not treated, and the control group might include units that were treated. And that means that in practice, the ITT is often lower than the TOT. So by contrast, the TOT effect is the effect of actually receiving treatment versus not receiving treatment, given that you were assigned to treatment. And as we saw, the TOT effect can only be derived from as the complier average treatment effect. And we can't get that complier average treatment effect unless we collect data on actual service delivery in both the treatment and the control groups. And once we have that, we can weight the ITT effect by the percent of compliers in the treatment group and get the TOT. Okay. Importantly, when there is no non-compliance, either in treatment or control, the ITT effect is equal to the TOT effect. That's because all subjects are compliers, and the ITT is an estimate of the complier average treatment effect. So an implication of this is that good research design always makes very strong efforts to encourage or assure compliance to the assigned treatment regimes. So first, you try to mitigate non-compliance in the control group. You don't want people in the control group taking up treatment. And one way you can do that is to have a fairly unique treatment that nobody else is doing, and nobody could take it up outside the study context, but often treatments are widely available outside the study. And so what you have to do as a researcher is to assure that the control group units in your study don't adopt the treatment either prior to or during the study. So that procedure is important to trying to get total compliance to the control group regime, which is absence of treatment. Non-compliance in the treatment group is a bit more difficult to control. So under normal conditions of practice and in many experiments, units sometimes agree to receive treatment and then just later on decide, nope, I don't want treatment. Given human subjects protections, an experimenter cannot force a unit into treatment. And so there is often going to be a small percentage, hopefully not a large percentage, of non-compliance in the treatment group. But you do all that you can to mitigate that kind of non-compliance as part of your study protocol. So researchers and policymakers, for that matter, often ask, well, which estimate is more informative? Do I want the ITT or do I want to look at the TOT? And the answer actually depends on several factors. So the first thing is that the ITT involves fewer assumptions than estimation of the TOT. Remember, the IOT is just about assignment to treatment. I don't need assumptions about, compliers and never takers and notifiers and so on. So the ITT is generally preferred in the scientific community because it involves fewer assumptions, and it is always reported in the scientific community because it's a very trustworthy estimate, especially under random assignment. However, if the data on service delivery show non-compliance, then the reporting of an ITT versus a TOT will depend on several additional factors, including the purposes of research, the research design, and how compliance was measured. So let me talk a little bit about that. Concerning the purposes of research, if the concern in the research study is with the efficacy of the treatment as received, then the TOT estimate is the preferred estimate. If you really want to know whether receipt of treatment is affecting the outcome, then you need the TOT, because the ITT is just telling you the effect of being assigned to treatment, and in the face of non-compliance, the TOT is being watered down. However, if you just want to study the effectiveness of a program that's operating at scale, where non-compliance is kind of a normal state of affairs, then the ITT effect, I have TOT, that's a typo, the ITT effect is probably preferable, because the ITT effect is the average effect on outcomes that would be expected under normal conditions of practice. It's sort of, if we encouraged people to, if people took this up under normal conditions of practice, this is the effect on average that we would see. That's what the ITT is telling us. And from that perspective, the ITT is actually a very relevant piece of information about intervention effects under normal conditions of practice. So in effectiveness trials, I generally prefer looking at an ITT. In an efficacy trial, I might want to look at the TOT effect in addition to the ITT. The utility of the ITT versus the TOT can also depend on research design. So if, in fact, an investigator assured complete compliance in both treatment and control, there's no compliance problem in the study, the ITT and the TOT are the same, and you don't need complex assumptions involved in estimating a TOT. You look, you see no compliance, you can estimate the ITT, and in fact, it will be equal to the TOT. And so, a good policy is to assure compliance, and if you do, then you don't need the TOT. The ITT is fine and is actually expressing the effect of treatment on treated. The second thing to know is that the strategy for estimating the TOT effect that I just presented to you requires random assignment of units to treatment and control. Otherwise, you can't make these assumptions about equal distributions. So absent random assignment, the approach that I just discussed to deriving the TOT estimate is not possible, and you're going to need a bit more complex statistical analysis, which will involve even more assumptions and so on. So the TOT estimate, this is why people really favor random assignment, is it allows a fairly simple way to estimate TOT. The third thing that you ought to consider when judging between an ITT and a TOT is how compliance was actually measured. So notice that in the strategy for estimating the TOT effect that I presented in this lecture, I measured compliance as if it were an all or nothing or binary state. But, it's often more reasonable to think of compliance as a kind of continuous and multi-dimensional variable. So compliance might be dosage, for example, or compliance might, you might have bought this service, but not that service, and that's the multidimensional case. So estimating TOT effects in the face of partial compliance is more difficult than estimating TOT effects where you assume that compliance is binary. And this kind of partial compliance problem is an area of ongoing research. There's lots of different ways to try to handle the problem. And if you're interested, you should consult additional resources. So we have the first thing is we're looking at assignment to treatment versus experiencing the treatment and trying to estimate the effects on outcomes. The ITT is estimating the effect of assignment to treatment. The TOT is estimating the effect of receipt of treatment given assignment to treatment. Okay, so that's the ITT versus the TOT. The ITT is the simpler estimate to achieve because it relies on fewer assumptions, but occasionally you want to see the TOT, especially if compliance is a real problem and is expected to be deflating your ITT estimate. So the next thing I want to talk about is conditional average treatment effects. So we've been assuming that treatment effects are uniform across units. But what I want to do now is relax or at least test this assumption by using subgroup analysis. So suppose we think a treatment will have different effects for different subgroups of people or organizations in a study, where the subgroups are defined by pre-treatment covariates. So, this is a big problem in healthcare. So here's some kind of hypothetical examples. There actually is some evidence to support treatment heterogeneity here. But supposing you suspect that interventions that are trying to promote weight loss in order to reduce diabetes have larger effects on men versus women. So you expect an intervention program to have one effect on men and a lesser effect on women, or you have you're trying to reduce blood pressure and you have an intervention and you find that people older than 60 respond well to this intervention, but people younger than 60 do not. That's another kind of sort of treatment heterogeneity problem. In education, you might think that interventions that manipulate PLC strength in order to improve student achievement have better effects if the teachers are higher quality. So you have high quality teachers with a lot of high quality, schools with a lot of high quality teachers, schools with a lower quality of teaching, and you speculate that the intervention is going to have different effects in these different types of schools. Or you might think, okay, I have an intervention that's going to encourage open-ended and problem-focused teaching, but I think that the effect of that might be greater if students have already acquired basic skills as opposed to not acquired basic skills. These are just examples of treatment heterogeneity across subgroups that you might theorize exist. So if you have hypotheses that treatment effects vary across subgroups, then you might want to estimate what's called a conditional average treatment effect. And that's simply the familiar tau average calculated for units whose value on some pre-treatment covariate X is small x. So a table below shows this. Supposing that the pre-treatment covariate is categorical, male or female, high income, low income, some ethnic category. If we subset the data into two groups, we can represent the data for calculating a CATE in tabular form. So look at group A has 100 people, group B another 100 people, 50 in each group assigned to treatment and control, calculate their mean outcomes, and then calculate calculate tau average conditional on what group the unit has been assigned to. And what we see here is in group A, the treatment effect is 30, and in group B, it's 40. And this is initial evidence of treatment effect heterogeneity, or of a conditional average treatment effect. And again, as I described there, weighted averages can be used to recover the ITT from this kind of table. Now, most people actually estimate the statistical significance of that difference between groups in effect size using linear regression and some kind of canned statistical program to estimate the conditional average treatment effect. So I'm going to spend a minute here discussing to you how that gets done. In the linear regression framework, the statistical model for the intent to treat effect would regress unit outcomes yi on treatment assignment zi and the covariate of interest xi. And if that's a categorical variable and there's two groups, it's just a dummy variable. In this model, beta is the ITT effect. And in this regression equation, it's assumed to be constant across everybody. And we've put the xi in there simply to adjust the effect for sample composition. It's basically like an adjustment for sample composition, but the average effect is beta. Now, if we want to allow the treatment effect to vary across values of x, then we add an interaction term to the regression. So now we have a new term that is a new effect, delta. And so the interaction effect is in fact delta. And if that is statistically significant, then we conclude that there is indeed a conditional average treatment effect, and we can go about graphing that effect for both categorical and for continuous variables. So now you can do this. Let me just explain here in a minute how you get the table that I showed that was showing conditional average treatment effects from a regression analysis. If Z, the treatment indicator, is 0 for control group and 1 for treatment, and if X is 0 for group A and 1 for group B, then we can easily recover the values I showed you in the table for treatment effects from the regression model. So the mean outcome for group A when not treated is simply alpha in the regression model. The mean outcome for group A when treated is alpha plus beta. The mean outcome for group B when not treated is alpha plus gamma, and the mean outcome for group B when treated is alpha plus gamma plus delta. So, those of you who want to spend some time seeing that, but point is that the regression model is recovering the information I showed you in the table. You can use the statistical software to show a kind of a chart where the conditioning variable is categorical. You can get the statistical software to produce graphs of these interaction effects. Here, let's just suppose that group A is urban and group B is non-urban schools, and we have some treatment going on in these different types of schools. And from the regression analysis, we recover these effects, and then we plot them. And so the data here are this: that each dot in that graph shows the treatment effect for a different subgroup. So for the urban units, it's about 1.5. For the treatment, for the non-urban units, the effect is about 7.5, and the difference is 6. Then the lines that run through those are the 95% confidence intervals, which those of you who know regression analysis will know is plus or minus 1.96 standard error of the estimate. And what this chart shows you is that while we observed some differences, the interaction effect is not significant since the 95% confidence interval overlaps with 0. And so that's how you think about statistical significance. If the data are continuous, what you're plotting is something on the order of a sloping line, a slope that shows how, for example, in this case, the size of the treatment effect will vary by the average years of teaching experience in a school. And you can get the dotted lines, the confidence interval, and that will show you how what the expected values are at different values of the conditioning variable. Very useful thing to produce. Now, I should say this. There are a bunch of issues involved in estimating conditional average treatment effects when the conditioning variable is continuous. One is, you'll notice going back that the line plotting those effects is a line, but it may well be that the conditional treatment effects are not linear. A linear regression is going to make them linear. And so if it's not linear, then you have sort of misspecified your model. And so a solution to this is to generally bin up the continuous variables. Say, create categories of schools, for example, in the years of teaching experience. Say, I have schools that have an average between 6 and 8, 9 and 12 and higher. And if you are now using categorical variables, even the linear regression is going to be able to pick up and express these non-linear effects. So in general, it's probably a good idea, and I hardly ever recommend this, but for continuous treatment, for conditional average treatment effects, it's probably good practice to try to use the conditioning variable as if it were categorical, not continuous. A bunch of other issues. Whenever the variable, the x, whatever x you're using, remember that it wasn't randomly assigned to the units in the study. And so there can always be confounding. That is, some variable other than the conditioning variable is associated with both the conditioning variable and the outcome, and that's going to cause you to see this conditional effect, but the conditional effect is actually not causal. So you should always report these cases as descriptive data, not as a causal analysis. It's important to remember that these conditional average treatment effects are always based on smaller samples than your general ITT effect. And because of that, they're going to lack statistical precision. And your study is going to have much lower power to detect the conditional average treatment effects than it is to just get the average treatment effects. It's important to remember that if you have multiple categories that you're comparing, you're engaged in multiple comparisons, and you have to adjust your p-values, your significance tests, to take these multiple comparisons into account. And so it's my opinion and my advice to you that unless you have really strong hypotheses about conditional average treatment effects, or it's a burning issue in your mind, you probably should avoid estimating Kate's. But if you really think it's important to estimate a conditional average treatment effect, then you ought to design your study to have sufficient power to trust the effect estimate that you get. And finally, I just want you to note that if you start looking at conditional average treatment effects in the literature, there is an emerging literature that is trying to figure out exploratory techniques for discovering treatment effect heterogeneity. And it's really an interesting literature because it relies on what my colleagues over in the statistics department call, quote, modern approaches to data exploration, Bayesian regression trees and machine learning techniques and so on. And so, if you're interested in this and want to do it as an exploratory kind of thing to do, realize there's a rapidly expanding literature that you need to get in touch with. So, okay, we've done the difference between the ITT and the TOT. We have discussed conditional average treatment effects, I would now like to talk about average causal mediation effects. So let's begin by talking about what's causal mediation and why is that even relevant to testing program logic models. So again, recall that a program logic model is an implicit causal model. And within that logic model, we assume that service delivery, the treatment, causes certain implementation behaviors and processes, and that those implementation behaviors and processes, in turn, affect program outcomes. And so we have a little causal model. It begins with the treatment. Service delivery has a direct effect on program outcomes, but we also assume that service delivery affects implementation behaviors and processes, and that it's through that path that the program outcomes are being changed. And so what mediation analysis allows us to do is examine each step of this causal diagram to see if, in fact, service delivery is related to implementation, if implementation is related to program outcomes, and if, when we take into account the effect of implementation behaviors and processes on outcomes, our effect of service delivery is diminished or explained away. And if we find that there is a strong effect of service delivery on implementation behaviors, that's great, because that's what we want. That's a confirmation of our program logic model. If we find implementation is having substantial effects on program outcomes, that's great, because that confirms our logic model. And then the dissipation of the direct effect means we really have a pretty good understanding of why our program works. So that's the relevance of causal mediation to testing a program logic model. Now I'm going to move away from that and go back to some general terminology that's used often in the mediation literature. So now X is going to be service delivery, the treatment, the so-called causal variable. Y is always like the outcome. And we're going to see, we begin in mediation analysis with a simple hypothesis, the akin to estimating the average treatment effect. We assume X, the treatment, affects Y, the outcome, and the size of that effect is expressed by the coefficient, usually regression coefficient, C. Okay, C, this effect from the first analysis is called the direct effect in this literature. Now, we think there's some third variable, which in this literature is often denoted M for being a mediator. In our case, we're thinking this is the mediator is implementation, that mediator is caused by the treatment X, and at least partially explains away the effect of the treatment on Y, such that we now have three regression coefficients: A expressing the effect of X on M, B expressing the effect of M on Y, and C prime, which is the new effect of exposure to treatment on the outcome given the mediator. Okay, so that's the basic setup and terminology. Now here's some next two slides, warning, are very dense, but I'm going to read them to you anyway. You know, they're dense because I'm hoping if you're really interested in this problem, you'll go back and study this. So the issue is this: if and only if, that's important, the two causal models that I showed you in the previous path diagrams are correctly specified, then the causal effects A, B, C, and C prime can be estimated from multiple regression analysis that takes place in 4 steps. So the first step is You take data from both treatment and control and show that the treatment is correlated with the outcome. Okay, it's just like, you do a regression of y on x and you get the estimate C. In our case, this is probably the ITT effect estimate that we get. And the first step is to show that, in fact, there is an effect of treatment or assignment to treatment on the outcome, because if there isn't, there's nothing to be mediated. So that's step one. And if you don't have that effect, there's very little reason to be engaged in mediation analysis. I'll talk about some conditions under which you might want to do it. Then, using data, again, from both treatment and control units, you show that the treatment indicator X is correlated with the mediator, where M is now the outcome variable and X is the predictor. So here what you're doing is you're regressing indicators of implementation behaviors and processes in the treatment and the control group, and you're regressing those indicators on whether or not a unit was exposed to treatment. And you want to show here that, in fact, exposure to treatment or assignment to treatment increases the kinds of implementation behaviors that a program wants to see. And you estimate the effect A that I showed, and that would show, in our case, any positive effect of A would show that the treatment, in fact, is affecting implementation behaviors in units under study. Then, again, using data from both treatment and control units, you want to show that the mediator affects the outcome variable. So now the outcome variable in step 3 is outcomes, program outcomes. You regress program outcomes on both the treatment indicator and the implementation indicators, and you get a new effect B, which is the effect of implementation or the mediator on the outcome, and a new effect C prime, which is the effect of the treatment indicator on the outcome net of the mediator. And the point of this would be to show that, in fact, implementation is indeed correlated to outcomes, and the A and B effect are going to, when multiplied by each other, express just how big that mediation effect really is. And C prime is important to look at, because if that effect goes to 0 or is getting reduced, then we can say that M, in our case, implementation indicators, actually are mediating the effect of treatment on outcomes. Okay, this sounds great. And it's like, why wouldn't I do this? Well, one reason is there are many, many assumptions going on here. Recall that I said at the outset of this little presentation that you had to assume that the model, the regression model you were using, was properly specified. Well, that includes a number of assumptions, only some of which can really be tested. So the no reverse causality assumption, right, which is like an assumption you have to make whenever you interpret a correlation as a causal effect. I think in these kinds of studies, it's pretty easy to say, well, there's no reason for me to expect, especially under random assignment in the study design, that the mediator actually affected the adoption of the treatment. I mean, so that's out. I'm not worried about that. But you have to assume in mediation analysis that there are no confounders going on. And that's a much more difficult problem. So there's a lot of causal paths, and each of them have to be free of confounding. So we have to assume there's no some pre-treatment covariate that's affecting both assignment to treatment and the outcome, such that if we included it, our ITT effect would be changed. Now, if we're doing random assignment, then that assumption is a sensible one and we can proceed. If we're not, like in a quasi-experiment, maybe there's a problem here. The next is we have to assume that there's no pretreatment covariate that affects both assignment to treatment and the mediator, such that if I included that variable in the regression, my causal estimate of A would change. And again, in random assignment, that's probably not a problem because, if the treatment is randomly assigned, then any P is equally distributed across values of X. So I'm not worried about it. But if it's a quasi-experiment, again, or other kind of observational study, that kind of confounding can be present in your mediation analysis. Third assumption is there's no pretreatment covariate P that affects both the mediator and the outcome, such that when we include that covariate in the regression, the causal path B gets changed. And this is a problem. And this is a problem in random assignment studies and non-random assignment studies, because the implementation is not randomly assigned. And so something other than the treatment could be causing a change in the outcome. And failure to include that something in some other variable could be accounting for both the implementation and the outcomes, and not including that makes your B estimate wrong. And finally, and this is really important, this is probably my main objection to mediator analysis, there's no post-treatment variable, PT, that is affected by assignment to treatment and that affects both the mediator or implementation variable and the outcome variable, such that if I included it in the regression, the size of the causal path B would be different. And this is a problem for me because you may have measured only one aspect of implementation. So if your implementation is a very complex phenomenon with lots of variables, you probably have multiple mediators operating, and not properly specifying your mediation regressions for that fact is going to lead to a lot of specification error and a lot of biased estimates of the A and B path. And so for that reason, especially, it's very important to engage in what's called sensitivity analysis when you do these mediation analyses. And that's a topic, again, which is way beyond the capacity of me to talk about it today in short form. But if you do one of these mediation analyses, you need to know that there could be confounding, and you probably need to conduct and show the reader a sensitivity analysis to show just how much confounding would change the results that you're reporting for mediation. A couple of other things I'll briefly touch upon. You can read upon this by reading further on this literature, but you have to assume that there's very little measurement error in the way you measured implementation for that mediation analysis to work, because if the mediator's measured with a lot of error, it's unreliable, then the effects of B and C prime are likely biased. So that's a problem. Note that the mediation analysis that I just showed you assumes that the mediator does not interact with the treatment or any other variable. It's just a sort of straightforward thing. So, mediation analysis is the simplest form and isn't really allowing for interactions. You can allow for interactions, and now, your analysis is even more complex. You should note that the research on these mediation effect analyses is advancing quite rapidly. And, there are structural equation models for handling the measurement error issues that are involved here, and the causal inference literature is beginning to elaborate this mediation framework using the assumptions of the causal inference literature as opposed to the regression literature. But a major conclusion that I would draw from this is that mediation analysis involves a lot of assumptions. And there's always, in fact, often the possibility that those assumptions are violated in a given analysis. And so when you report these mediation analyses, you should probably report them as both exploratory and correlational, not as causal. Okay, these are exploratory analyses. Okay, so I'm at 90 minutes, but I need to summarize. So let me do that kind of briefly, and then we'll open up for questions. Okay, the point of this lecture was to discuss was that researchers need to gather data on each step in a logic model. And then what I wanted to show you is how such data can be used to estimate various kinds of treatment effects, and how those treatment effects inform the confirmation status of a logic model. In what follows, I'm going to show you how first data on service delivery data can be used to assess compliance and what that implies for the kinds of treatment effects that you can estimate. Then I'm going to talk about how data on implementation can be used to to study how service delivery affects implementation, and how implementation affects outcomes, and how that data could or could not be used in a mediation analysis. And then I'm going to continue to discuss how you might use service delivery and implementation data to inform or interpret your simple outcomes analysis. So here, the one point that I'm making here is that any good research study of an intervention needs to examine compliance to the treatment regimes in the study, and that is done by collecting data on service delivery, not only in the treatment group, but also in the control group. So now we have such data. We have data on the services that were delivered or treatment uptake in both treatment and control. And the first step is to just look at some descriptive data and ask, to what extent were treatment services actually delivered to the units assigned to treatment? And that's just a compliance issue, but it's also, do you have an intervention that actually succeeds in delivering services to the treated? The next thing you want to know is whether or not units over in the control group are actually receiving the same services outside the study or by some other means. You can then conduct a very simple ITT analysis where compliance indicators are the outcome variable. I call this, and will in the next lecture call this, the service delivery contrast. And that addresses this question. To what extent was receipt of treatment services more prevalent in the treatment group than the control group? Now let's imagine what kind of data we might get having collected, what kind of outcomes we might experience having, or patterns of findings we might experience having collected such data. So in the ideal world, in a good experiment, there will be little or no non-compliance. That is, treatment services will be delivered in the treatment group, and you won't have a lot of control groups that are also getting treated. And that means that all treatment groups got the treatment, no control groups, you have no non-compliance. If you have no non-compliance, the ITT effect is very serviceable, and there's no need for more complex analysis. On the other hand, if non-compliance is present, don't drop the non-compliers from your outcomes analysis. Instead, interpret your ITT effect in light of non-compliance. And then if, and only if, the purposes of research call for a TOT analysis, that is, you're engaged in an efficacy study or you're truly uncertain whether the treatment, has an effect because there's so much non-compliance going on. And if you can easily measure non-compliance, then you might want to move to the more complex and assumption-laden TOT. Next, any good study of an intervention program needs to examine implementation processes both in the treatment group and the control group. So to do this, you have to collect data on the same set of behaviors and processes as these occur in both the treatment and the control group, and you have to use the same measures. It is not sufficient in a study simply to measure what's going on in the treated group. You want to also measure whether similar things are going on in the control group, because that's going to give you leverage for estimation of further kinds of stuff. So supposing we now had collected these data, the first step is to analyze descriptive data on the presence of these behaviors and processes in both the treatment and control groups to address the following question. To what extent did units assigned to treatment actually faithfully implement the program desired behaviors and processes? The second is, to what extent did units assigned to the control group display similar behaviors and processes? And then you can conduct what I'm calling the implementation contrast. You just do estimate an ITT effect where implementation is the dependent variable, and you answer the question, to what extent did implementation behaviors and processes differ across the treatment and control group? So let's talk now a little bit about patterns of findings. Ideally, this analysis, this implementation contrast, will show the treatment group has higher levels of implementation behaviors and processes than the control group. And that demonstrates not only that the sort of intervention logic model is working as predicted, but it's needed because without intervention, nobody's doing these behaviors and processes that you're trying to promote. If some units in the treatment group aren't implementing a program, then don't drop them from the outcomes analysis. Keep them in the ITT analysis of outcomes. And if you get a low effect, interpret that effect in light of reduced implementation. Then, if implementation is well measured, that is, you have a fairly reliable estimate with low error, and you have like a single composite indicator, you might want to try one of these ACME analyses. But again, recall they're assumption laden, and there's a specification error is probably present in this. And so whenever you report it as a descriptive analysis, and you always report a sensitivity analysis. And finally, you need to examine program outcomes in both the treatment and the control group. So you collect the same outcome, and you begin the outcomes analysis always with the ITT, and you always report the ITT effect. I would recommend that you conduct the conditional average treatment effects analysis only if you have strong or theoretically driven hypotheses about treatment heterogeneity. And I would recommend that if you're really interested in it, you design the study so it has sufficient power to detect those effects. And finally, you report the TOT effects only if they're truly important and relevant to the purposes of your study. So ideally, your study procedures have assured that the treatment was received. There's a lot of compliance in the treatment group. There's little non-compliance in the control group. And so the ITT estimate looks like the TOT estimate, and you don't really need to do the complex TOT estimate. On the other hand, if there is evidence of non-compliance, then you might want to move to this TOT model. Okay, so I have already expanded the last part of this lecture, the last set of slides really sort of take you through what to do when you see an ITT and whether that warrants, whether particular patterns of data. I'll let you read that on your own. I think the time has come for us to move to the question period. So let's go ahead now. I'm going to open the floor for questions. So go ahead and use the Zoom question chat box, and I'm taking questions now. So I have one open question, which says, in the case, why are the always takers 0? Why in ITT effects, why is 0 always takers 0 for both treatment and control group, not 5? I'm going to have to go look at that. That might be some kind of a typo, perhaps. So let me go back here and look at this. So I'll just explain this table again to you. Let's explain it. So always takers in this they don't present you with a counterfactual. Notice that the always takers are always treated. So I can't take an always taker and compare an always taker when treated to an always taker when untreated. And because they were treated, and we have that the assumption that the treatment effect is always the same regardless of assignment to treatment or control, the tau average for always takers is always 0. That's what the table is showing. And the same will go for never takers. They don't have a counterfactual. They don't ever take. So I put them in the treatment group, they're not treated. I put them in the control group, they're not treated. They have no counterfactual. And so the effect estimate here is just basically 0. So that's the idea going on there. Hope that explains that. So the next question here is, supposing 2 treatments were adopted and we show a big difference. I suppose that's a big difference on ITT or TOT effects. How do we reconcile the difference? Are there criteria to consider to determine which treatment is generally working? And is there a way to countercheck? Okay, this is excellent. So supposing instead of a single treatment, we are now considering 2 treatments. And supposing we get 2, we have intent to treat estimates of the effects of assignment to treatment on outcomes for these 2 programs. And one of these programs has a very low ITT and the other one has a high ITT. And so the question here is, look, should I really believe this? How should I look at these data to try to figure out whether I believe this or how informative it is? So my answer to that question would be, let's go back now and begin to look at patterns of service delivery and implementation and see if perhaps they explain some of the differences. So supposing that the intervention that had a low ITT, also the study was conducted where there was lots of non-compliance, then I begin to wonder whether the actual effect of the treatment on treated was not underestimated due to non-compliance both in treatment and control. Okay, so I might begin to discount the ITT and want a TOT. and make my comparison on the TOT estimate, not the ITT estimate. Or suppose that in the one that had the low ITT had poor implementation. Okay, then I might begin to say, well, maybe implementation failure is what explains the low ITT. I believe in this intervention, or I believe that what the implementation model is a good one. I'd like to see it tested. You might, although you don't really have anything to explain, but you might try the mediator Acme kinds of models to see if I produced what I say should be produced, it really does affect it. And then the problem in the low ITT intervention program is that it's not reliably producing implementation outcomes. So I hope that explains how you might look at two different treatments, both intending to affect the same outcome using different strategies, and I want to compare them. And the question is, do I believe the ITT effects? And so what I said is appeal to the other data being reported on compliance and implementation, and that can help you determine whether or not you really trust that ITT that you're seeing, and can help you explain how the intervention is functioning. So okay, that's my answer to that question, which I think is an excellent question. So the next question is, what types of measures or instruments do we use for data collection before the analysis of a treatment effect? Okay, the problem of study instrumentation is a difficult one, but in general, at a very abstract level, you should have instruments that measure whether or not the services that define the treatment were delivered to units in the treatment and control group. You need service delivery measures. So if the treatment is we're going to give a series of 5 workshops, you need to collect data on whether or not those 5 workshops were delivered at the unit sites that are in the study, and whether or not the same kinds of workshops, or even the exact same workshops, were delivered in the control group. Then you need measures of implementation. And my general advice about this is you've specified in your logic model what organizational processes need to be in place for the intervention services to work, what the intervention services are trying to change about the way some organization is structured and functioning, or behaviors that you're trying to change as a result of this. That's the implementation model. You need to measure those in treatment and control. You can do that with survey responses, self-reports of whether people engaged in this. You can do this with observational measures. You can go in and observe. Because we're engaged in quantitative analysis, you need to make these measures subject to quantification. And they need to be the same in the treatment and the control group. And so my general advice is to avoid using buzzwords for describing something that are unique to the treatment, and try to make them so that people in the control group can report that they did do these things, and people in the treatment group are reporting that they did these things without the bias of using the desirability bias of using terms that are used by the intervener themselves. So, and then you need to measure the same outcomes. Now, like, can I get more specific than what I just said? Well, no, because measures development is an important step in research, and you know, I would be happy to provide a lecture at some point about that, but you know, it's a problem. But you know, the point is always measure service delivery, always measure implementation, always measure outcomes. And if you do, then you're in a position to estimate the kinds of effects I'm talking about. So that's my question. It says Tom wants to answer this live. I'm not sure I'm going to let Tom answer that live because I'm going to go to the next question. So this question is, what do I think about using artificial intelligence in order to implement effective programs in different sciences? I don't have an opinion about AI. I mean, you know, my point would be that if you had AI increasingly drives algorithms for instructional programs, and so you know, my thinking is that, you know, I'd like to see how those AI programs work in practice, and the kind of research that I'm advocating can be mapped easily into a study in AI interventions based on AI that are determining instructional treatments. Okay, now let me go to the next question. The next question I'm going to address is, can the researchers obtain an objective measure or cutoff score to identify whether the units are assigned to the always taker in the control group? Well, the assumption here is that, let's just work through this. The only people who are taking up treatment in the control group are always takers. So I don't have to worry about compliers taking up the treatment because the compliers aren't taking up the treatment, right? The only people in this little scheme who take up treatment are always takers. So the question is, can I get an objective measure or some cutoff score that says, yes, I took up treatment? And by the way, if I have that, I'm using it in both treatment and control. And, you know, it's in my own personal experience, it is often fairly obvious in a study who either took up or didn't take up treatment. Now, implementation is a different story. There's a lot of variability in implementation, but you know, in my experience, the units in the treatment group usually either fully comply or just say, hey, you know what, we're not interested. But you know, if there's some variability in this, you know, you could set up a cutoff score. I wouldn't have a problem with that if you could justify why you made that, why you made the break where you did. I'd be happy to do that. But the important point is that it's a good question in the following sense. When, you know, you need to have some way to do this TOT analysis using the strategy I advocated for, you need to have a binary variable. You either did or didn't take up the treatment, and can you make a cutoff for that? You know, I would say usually, yeah, it's not that hard to do, or you can make a good case for why you did it. And so that's my answer to that. Okay, so that's, I don't have any more. It's just a kind of thank you. Let's see. How to deal with missing data. Here's a question below the thanks so much. How to deal with missing data or poorly treated data gathering among the treatment group. Right, so missing data is a problem. My let me just say the following about missing data, okay? When you do research, when you conduct research, when you're the principal investigator of a large study, you work extensively to prevent there from being missing data. Now, if there is missing data, I mean, you can never force somebody to comply to the research protocol. And if there is missing data, then I'm pretty sure that the questioner here, and many of you know, there are many ways of performing statistical estimations of relationships among variables in light of missing data. The usual approach is to impute, either multiply or using some mean plugging procedure to make sure that or sometimes just estimating things and having a mean plug with a dummy variable. Anyway, there's a lot of ways of coping with missing data in the measurement side of things. For the X's, the independent variables in a regression analysis, and a general point I want to make to you is, don't drop people who have missing data. As much as possible, try to keep people with missing data or units with missing data in your study design. Now, missing on the outcome variable is a different problem. Now, there are people who, by the way, advocate for imputing values of the dependent variable, but most people don't like that and will look askance at you if you do impute the value of the dependent variable. And so let's say you don't. Well, if they're missing on the dependent variable, you have a problem of study attrition. That problem is one that I am going to discuss the next time we lecture, what the tolerances are for attrition. But you know that, what you're worried about attrition on the one hand, and you're worried about differential attrition on the other hand, where differential attrition is you have more missing data in one group than another, and you're not really sure whether that's biasing your results. And so the general rule of thumb is, if you can't collect a piece of data the first time, go back. And if you can't collect it the second time, go back. Just keep trying to collect data so there isn't a lot of missing data. And studies that have a lot of missing data are poorly conducted studies, and people should discount the results. There is going to be some missing data, okay? And the thing that I worry about most is missing data on outcomes, because I'm not going to impute those data. And then I have an attrition problem in my study, and we'll talk about attrition next time. Okay, so that's the answer to that one. A question here is, why is the treatment group more difficult to control? Well, in fact, maybe I misstated that. Okay, so what we're talking about here is we're doing a study, and we want compliance, and we have non-compliance possibilities over in the control group. But my argument was, there's some ways that I can sort of mitigate against that. One is, like in experimental drug trials, you can't get the drug unless you are enrolled in the treatment arm. So that's immediately, that's a way to control access so that members of the control group can't take up treatment. Now, under some conditions, for example, if you were an intervention program, you could say, for the next period of time, I'm not going to give the intervention to anybody except those who I randomly assigned as part of my study. Okay. Most people don't do that, but most of these interventions that I've studied, by the way, in the real world, even when they're widely disseminated, you can find plenty of schools that don't have the money to take them up on their own or aren't in a geographical region that serve. So it's pretty easy to maintain a control group that's not exposed to treatment. Just there's not a lot of resistance. There's not a lot of control group members raising their hand and saying, I want the treatment. And by the way, as a condition of joining the study, you've agreed not to take treatment unless you're allocated to the treatment group. Okay, so on the other hand, over in the treatment group, you can't force people who are assigned to treatment to take the treatment. And, it is not uncommon for a few units in the study. Yeah, principal changes or a long time intervenes between the day you planned this study and the day you implemented it. And some people simply decide, look, I'm sorry, I don't want to do this anymore. And I'm not going to do it. I'm not going to be treated. Then the problem you have is a missing data problem in the following sense. If somebody says, look, I don't want to take the treatment, and we're under human subjects protocols, I can't force you to take the treatment. What I want to do is still collect all the data that the study requires, even though you're in the treatment group and not taking the treatment. Okay, that's a central point I want to make to you guys about this. Just because you're a non-complier doesn't mean we stop collecting data on you. We try to keep the data going, the data collection going, even in cases of non-compliance. Okay, so that's my answer to that one. So this is a related question about what I mean by unique treatment. And, could I just give some examples? So the unique treatment, the way it's done in drug trials, again, is this is an experimental treatment and you can't get it by law unless you're enrolled in the treatment arm. That pretty much assures non-compliance is taken care of over on the control group side. In our world of education where we're developing interventions, your intervention could be unique in the sense that it's doing something that no one else is doing, that is delivering a set of unique circumstances, unique services that no one else delivers. Or on the other hand, you could be not, your thing could be not that unique. That is, you could be delivering services and there's 12 other competitors who are delivering the exact same services. So then that's the uniqueness problem. How different is the set of services you deliver than the set of services that somebody in the natural world might be accessing? Because that'll drive compliance over in the control group. I'll give you an example. You wanted an example. So I am aware of a study in schools in Chicago which examined what was the effect of using classroom observations as part of the teacher evaluation process. What was the effect of that on student learning? And so they had a treatment for this, and they randomly assigned it to schools. And at the end of the study, they, like anybody else, measured both service delivery and implementation. They were good researchers, and what they found was that over in the control group, there were lots of schools that had exactly the same program operating. That is, they were using classroom observations to evaluate teachers. So this was happening in both the treatment and the control group. And moreover, they were doing that because they had been delivered services by several other organizations, which were teaching people roughly what this intervention was. So that's how you, and so what they find is there's no effect, but really there's no ITT because they have a compliance problem. Okay, so that's the unique thing. And so, you want to be that's why I was saying what you want to do is make sure that the control group isn't exposing itself as a natural process to the treatment you've developed. Well, if nobody else is offering the treatment, they can't, unless you stupidly somehow sell it to them outside the study protocol. So you get the point. That's the uniqueness point. I'm trying to get to, okay. Oh, so here's the question about cohort implementation and whether we should do Kates for that. Yeah, I suppose that you could estimate Kates by cohort. I would note that is, instead of estimating the average treatment effect across all cohorts, you break the study population into subgroups composed of different cohorts. I would just caution you that I don't know, why you would want to do that. It could be that you have some timing hypothesis. Later cohorts should have higher effects because people are getting used to the treatment and so they should be delivering it better. That may be a reason, but when you break your total sample into subsamples, you've effectively reduced the sample size on which you're estimating an average causal effect. Now you have subgroup tau averages that are the basis of your data. You don't have the same precision or power as you do when you try to estimate it across the whole sample. So that's my comment about that. If you're going to do this kind of Kate analysis and you have a strong theory, make sure you design your study for sufficient power to detect conditional average treatment effects. Okay, the next question is, if we have population data, but due to missing data, can we treat the data as a sample rather than a population and run inferential instead of descriptives? So, okay, this is a very complex question. I'm going to need to process this in my mind out loud before I answer it, so bear with me here. The first is the question of population versus sample of population. And so, like in general, I don't think any study that you're doing assumes that you have the population. You usually are assuming that your study is of a sample of people, and there's some larger population out there that could have been in the study but weren't in the study. Okay, that's the difference between population and sample. If you have a population, everybody, there is no need for inferential statistics because you have a population, so you've got the parameter, not the estimate. Okay, so the only condition under which you would have the population, I suppose, would be that no one, well, I just can't imagine it. I guess I was going to say, if you said, well, okay, this treatment is only going to be ever delivered within this set of schools, and now I'm going to randomly assign them to treatment and control, then I have the population. But even then, I mean, I could have, and then the way people handle that problem is they usually use randomization statistics or well, like forms of randomization statistics, not inferential statistics, to calculate all the p-values. So that's the second part of this. The missing data issue is I'm not sure that I guess the question here is really for me about whether what kind of inferential statistics are you using and what kind of assumptions are you making about your population? So I think most people in our world use inferential statistics, which make a lot of assumptions about notional populations from which I drew a sample. And in fact, you didn't draw this sample either. It's just sort of a haphazard sample of people you manage to recruit. Okay, sometimes it's fairly carefully done when you have millions and millions of dollars, but certainly in exploratory studies, smaller efficacy studies, and often even big randomized field trials, you don't have a random sample of some known population. Lots of the inferential statistics that people calculate, however, make a bunch of assumptions that you do have this kind of thing, and about distributional assumptions of how the outcomes are distributed and so on. So I myself am a big fan of not using those kind of statistics and to using more non-parametric like randomization or permutation statistics to calculate p-values and things like that. They make less assumptions, and the assumptions are more appropriate to the sampling strategies that are generally used in this kind of work. That's something I didn't lecture about, could lecture about, might talk about a little bit. We will talk about sampling and generalization in the next lecture. So that's my answer to that question. And that looks to me like we have taken up all the questions, and we are about 10 minutes over time. So what I'm going to do now, I think, is just turn the session back to the organizers. So thank you, everyone. I appreciate your attending, and good luck to you until the next time.